Good morning, everybody, and welcome to the December edition of the Science Communication Webinar. I'm Van Stansel. I'll be moderating the presentation this morning. As usual, we're going to ask that you keep your cameras off and your mics muted. We are recording this to be posted on YouTube later. And if you have any questions, we ask that you go ahead and put those in the chat as Corey is talking, and he'll answer those at the end of the presentation. Today, we have Corey Dunn, who's the leader of the NC Co-op unit and professor at NC State University. Corey, welcome. Take it away.
Thank you, Van. Thanks, everyone, for joining me this morning. A sort of quick technical note, I got dual monitors going, and one just cut out on me. So luckily, I got my presentation pulled up on the other monitor, but y'all let me know if we run into any technical issues. All right, so I'll go ahead and get into my presentation. I have joined NC State's and North Carolina Co-op unit about a year ago. And so main motivation for me providing this presentation this morning is really just to provide a high-level overview of my research program and my role here at the North Carolina Co-op unit. I've traveled around the Southeast doing research in graduate school and as a research scientist for USGS. And so I decided to build this presentation around a couple main themes. The first is the tremendous biodiversity we have here in the Southeast. The second is the variety of river networks I've had an opportunity to work in. So I'm going to start with just overviewing the program. People have probably heard the term co-op unit or cooperative research unit. I just want to clarify, what is that? It is a federal, state, university, and not-for-profit partnership that was informally established in 1932. It's a direct extension of the North American model of conservation. If we go back to the 1930s, a lot of our wild game species have been completely decimated. And there was a real need to try to use the emergent field of wildlife management to sustainably harvest our species. But we needed some type of mechanism to train the future workforce to join conservation agencies and actually implement the science that goes into managing wildlife populations. So as a program, it's been around longer than the New Deal. It's as ever relevant today as it was back in the 1930s. North Carolina got its co-op unit in 1962. We pretty much all of our activities revolve around a three-part mission of the co-op program. The first is we do applied research to support the research needs of our management cooperators. And so I mentioned it's a federal-state partnership. The State Conservation Agency is a core and signatory member of each co-op unit. And so we do a lot of research support to help agencies better manage or at least inform their management decisions. Going back to the 1930s, the core mission was to train the future conservation workforce. So that's the second part of the mission. Since 1962, the North Carolina Co-op unit has graduated. I think we're up to 181 master's or PhD graduate degrees that we've awarded. With 81 of those coming since 2006. And so we're still training a lot of future conservation professionals, many of which work for the Wildlife Resources Commission. And then we provide technical support as the last part of the mission. Y'all will see me serving lots of technical panels. You'll see me lots of going out in the field with y'all. You'll see me in kind of lots of different places. And the reason I'm doing that is to fulfill that third part of the mission. The Wildlife Resources Commission is a formal cooperator. And so anyone should at all times feel free to reach out to me. I may not know necessarily the answer to a question, but I'm happy to serve as a soundboard and provide my time. After all, it's 1/3 of my job. It's a network. We're up to 43 co-op units. We've added 3 over the last few years. North Carolina Co-op units based at NC State right here in Raleigh or behind the head of Tuffy the Wolf there. So I want to shout out the other federal scientists who are at the co-op unit with me. I'm the leader, but I work really closely alongside a couple quantitative ecologists. They do a lot of wildlife work. The first is Jaime Collazo, and the other, the newest member is Nathan Hostetter. And then we are the three federal members of the co-op unit, but really the kind of the gold stars of the program are our numerous students and research assistants. Right now, all in, if you go over to the co-op unit, there's about 15 or so of us, with numbers ebbing and flowing depending on the number of projects we have. But if you come around summer when we're employing a lot of undergraduate students, there might be 30 to 50 or so people affiliated with the co-op unit. What is our role within this cooperative partnership? I don't do any management or policy decision making. I kind of viewed that as really the hard job. I exist in these sort of lower two boxes where I conduct applied research that ideally reduces uncertainty and helps our management partners make optimal decisions with regards to the critters that they're managing. I also do a lot of monitoring support, both in terms of developing monitoring programs, but also, we have at our disposal, small armies of strong-backed graduate students and undergraduates who can also go out and collect a lot of the monitoring data. But what I'm going to focus on today is how often at times there's this arrow between applied research and the monitoring program, in the sense that we can invest research and development into building better monitoring programs. And those monitoring programs, in turn, can allow us to ask better questions, better research questions that ultimately, at the end of the day, help inform those management and policy decision-making. So I mentioned, I've worked all across the southeastern U.S. My master's was in the Appalachian Mountains. My PhD was out in the Ozarks. I was with the Mississippi Co-op unit down in the Gulf. And I finally relocated back to the Piedmont, where I'm originally from, here at NC State. And it's a real it's been really amazing to have an opportunity to work with so many species across the Southeast. From this paper et al., or Elkins et al., just east of the Mississippi, there's well over 1,000 species of fishes, mussels, and crayfishes. Unfortunately, we don't have enough resources to fully understand life histories and do a lot of the population monitoring to be able to ideally, manage all of these species. So we're sort of perpetually in this situation of having high data deficiency for most of our species. And that all sort of comes to a head when we have situations where our hands are forced. A great example is the mega petition, which was lobbed in 2010. And this was a petition to list over 400 freshwater species in the Southeast on the Endangered Species Act. If you go through the 1,000+ pages of document here, about 48 of those species were fish, 46 of those species were mussels, and a whopping 83 species in the mega petition were crayfishes. So about 20% of the mega petition was just crayfish. That puts us in a situation where we really need to be able to efficiently collect data to inform some of these risk assessments. And we also need tools at our disposal that allow us to make informed decisions in the wake of uncertainty. And so that's what I'm going to try to highlight here with my talk overview. I'm going to present 3 different case studies across widely varying stream network sizes. And at the end, I'm going to talk about how all this information can come into a formal risk assessment. I'm going to start in the largest river in North America, the 10th largest river in the world, and that's the Mississippi River, and it's and the Missouri River, which joins it right at St. Louis. My PhD was funded by the Missouri Department of Conservation as a part of the Missouri Co-op units. They were really interested in understanding what species live in their non-wadable rivers. Existing sampling protocols typically emphasize a single gear, They're really developed as just kind of an extension of wadable stream electrofishing surveys. So the Missouri Department of Conservation recognized that they really weren't getting a lot of the species that are out there. So they funded me to develop an optimal way of sampling non-wadable rivers to try to detect as many species as possible. So I developed a monitoring program. I emphasized gear diversity that reflected all of the different river habitats that you might expect in a healthy river. We also put out 3 different passive gears that were able to fish overnight. So we're also sampling that temporal component to our river systems. And just to kind of a really coarse overview of kind of what this sampling protocol looked like, I'm just going to highlight this here in the Black River in southeastern Missouri in the Ozarks. And this stretch of river, this sort of 2.5 kilometer stretch of river, pretty consistently has about 76 species of fish. I know that because I spent well over a month sampling this section of river for my PhD, and we pretty consistently catch that. This is just a sort of overview, a typical river sampling protocol. It's typically a single gear electrofishing, may go for around 1 kilometer. Even that's a pretty intense electrofishing survey. And so the first thing I did is sort of said we need to break up effort. We need to distribute it across a longer stretch of river. So we're fully encompassing some of that lateral diversity that you can see there shown by the different gravel bars and off-channel areas. I went in with those 6 different gears. I actually spent years sampling with those full gears. And then I developed an analysis that uses a supercomputer, and it was able to deconstruct the full sampling protocol into each of the 287,496 different combinations of gear and effort that you could possibly do to identify the most efficient way to sample a river. And this is what we came up with. It's pretty much the most efficient gear, which is electrofishing, supplemented with kind of an optimal ratio of other gears that are able to kind of go in and sample these unique areas that that electrofishing isn't able to do. Using a protocol like this, we can probably spend usually about like 2-3 days on the river and pretty consistently catch about 74 of those 76 species that you'd expect to find out there. Okay, so now we have this really nice, efficient, and accurate sampling protocol for rivers. The second part of the Missouri Department of Conservation's question was, what's the role of our non-wadable tributaries for supporting large river fishes? This was kind of instigated because there's over the last, I would say, 20 or so years, there's been this shift to emphasize the role of tributaries in large river fish conservation. You can see this in terms of a lot of barrier removals that are going on in tributaries. There is some active restoration going on in tributaries. You see this with a lot of ecological flows. And the reason there's been this kind of, I want to say pivot, but a greater emphasis on tributaries is they're less interjurisdictional. And so oftentimes a single tributary will occur in a single state. And also our really, really large rivers, such as our great rivers, which are, have watershed areas greater than 250,000 kilometers, is that those are kind of locked in. Those are going to be managed for navigation, and it constrains our ability to do a lot of our restoration work. So there's been this kind of focus on, or at least emphasis on, understanding the role of tributaries for supporting our large river fishes. The best, maybe kind of, guiding document or guiding research that we had on how do you identify high priority tributaries was done by Preach et al. In 2013. And they had this really basic question of what tributaries have the greatest conservation value for large river specialist fishes. What's a large river specialist fish? There are some existing kind of traits-based classifications of really large river fish. Typically, the typical profile of one is a periodic strategist, really large-bodied, really long-lived. Oftentimes they're migratory, such as these sturgeon or these really big suckers like this blue sucker. But you can also have some small-bodied fish that specialize in really large rivers, such as the river darter. And so the main diagnostics that we use is that it's a species whose populations are centered in our great rivers, the Mississippi and the Missouri River, and their populations may extend up into the tributaries via direct dispersal for our migratory fish or some type of metapopulation dynamics for some of our small-bodied fishes. But either way, their distributions are centered for our study area, the Mississippi and the Missouri rivers. And so, Prach et al., there's very little river sampling data out there. There wasn't necessarily a database they could turn to try to predict high-value tributaries. And so they used a really coarse approach. They could go in, there's some existing estimates of annual discharge at the mouth of all tributaries of the Missouri and the Mississippi River. They also have some very loose best guess estimates of the large river species that may occur anywhere in the watershed of each tributary. And they more or less fit a regression relationship between discharge at the mouth and the number of large river species that have ever been reported within a tributary. And they found a positive relationship. It was actually pretty predictive. So it's a really useful tool for testing their hypothesis. But they can also use it in a conservation tool and use that same species discharge relationship to forecast up into tributaries the length of tributaries that are unimpounded and also have some type of minimum discharge necessary to support high proportions of large river specialist fishes. And so this is the predicted high value tributaries based on their species discharge relationship, which is really neat. So when I was starting my PhD, Missouri Department of Conservation had this great question, and they said, hey, what's the role of discharge? We saw that this paper, Prach et al. Kind of found that relationship. And I looked at it, I said, I think that's a really neat paper, but they're making this huge assumption that you can take that same species discharge relationship, which is fit at the mouth of a tributary, and project it into specific sites within the tributary. That's a major assumption that hasn't been tested. And now that I've got this really efficient sampling protocol, I want to go in and test it. The other assumption that the Prach et al. Paper has is they're assuming that it's solely, the number of large river species that exist in a tributary is solely determined by the discharge at the mouth of the tributary. And so I suspected that wasn't the case. I suspected that there are reasons why our mainstem fish are running up into these big tributaries, and therefore the availability of habitat may also influence the number of large river species we find within tributaries and the distributions of those large river species within tributaries. So I suspected we'd see kind of a relationship that looked a little something like this. So 2 research questions. Does discharge predict larger fish richness at sites within tributaries? And what other variables explain residual variation in larger river fish richness? Is it the dispersal distance from the main stem? Is there a cost to these fish having to swim up into these tributaries? Or is it available habitat you find within tributaries? So I set out to test this. I conducted, what really is a riverscape scale observational study. I found 2 tributaries that are within Missouri. One is a tributary to the Missouri River. The other is a tributary of the Mississippi River. The fauna that you will find in each of these 2 mainstem rivers is really similar, those being the Missouri and the Mississippi River. And then I conducted an almost identical longitudinal survey of the Grand River and the Merrimack River, covering the lower 200 to 250 river kilometers of both systems. Both of these tributaries and their upper stretches are 5th order. By the time you get to the mouth, they're 7th order. Neither are dammed, so this allows fish to disperse up into the tributaries. And both have pretty complex river networks. They both have larger tributaries within their own basins that come in right around the midsections of the main stems of the Merrimack and the Grand River. So this provides a lot of complex river network in both of these tributaries. So the Merrimack River is a classic upland Ozark River. 180 kilometers upstream of the mouth, you'll find a great smallmouth bass fishery. This is clear water, rocky substrates. And as you move downriver, you go through a pretty dramatic longitudinal change in habitat. By the time you get down to the mouth, the river is much wider. It's functionally kind of a backwater of the Mississippi River. It's very flat, very silted, very turbid. And we had 12 sites positioned about every 30 kilometers across the lower 250 river kilometers of the system. And we also sampled the principal sort of branches that come into, that feed into the Merrimack as well. The Grand River is the complete opposite. It is the same size as the Merrimack River, but this is a prairie river. 180 kilometers upriver, this river is brown, sandy, silted, very few rocks other than, some that have been added around the boat ramps. And as you go downriver, it's pretty much the same. Even 5 kilometers upriver, it's pretty much the same turbid, brown, sandy system. So very weak longitudinal gradients in habitat. Again, we sampled sites every about 25 river kilometers and sampled the lower sections of both main branches that feed into the Grand River. So we had a common pool of large river specialists. All of these species occur in the main stems of the Missouri and the Mississippi River. In Missouri, then altogether there were 37 large river specialists that we were hoping to potentially catch in these tributaries. And we ended up catching 29 of those 37. So about 78% of these large river specialists. We caught 18 of the 37 in the Grand River and 28 of the 37 in the Merrimack River. A lot of these species weren't even known to occur in these tributaries. So, I would say probably like a quarter of these are completely new records that people didn't even know about, that these fish were used in these tributaries. I mentioned that we actually saw a lot more of these species used in the Merrimack than the Grand River. In the paper that's associated with this, I go into a little bit more detail on this, but you can look to the species traits to kind of give you some clues about what's going on here, what's causing the differences between systems. If you break up the pool of species, so on the left here is the Grand River. There's 3 columns there. The far left is the pool of species that we did not catch in the Grand River. These are those main stem fish that did not, at least from what we could tell, weren't really used in the Grand River. The middle bar is the fish that we solely caught at the mouth of the tributary. So within the tributary, within the lower 5 kilometers, but we didn't catch them farther upstream. And the third column is the fish that we caught farther upstream. And what you'll find is if you look at the pool of species that weren't used in the Grand River, there's a disproportionately high number of those are lithophilic species. So species that require rocks to spawn on. As I mentioned, there's very few rocks in the Grand River. So it makes sense that those fish are not leaving the Missouri River to run up in the Grand River to find rocks, that the rocks aren't there. Opposite pattern, the Merrimack River. If you look at the fish that we didn't catch in the Merrimack River, but are known to occur in the Mississippi River, we find a disproportionately few number of those lithophilic species. If you go into the tributary of the Merrimack River, you catch a higher proportion of our lithophilic species. And the farther upriver you go, you get even more higher proportions of lithophilic species, which sort of tells us that these fish are making informed decisions whether to swim up into these 2 tributaries or not, or at least there's something ingrained in them that's causing them to make that swim. So question 1, does discharge predict large river fish richness within tributaries? So we're directly testing that Prachel et al. Relationship. This is our hypothesized expectation based on Prachel et al.'s paper. This is what we found. We found that, there is a positive species discharge relationship. So that Prachel et al. Paper is really useful for predicting the number of large river specialists you might find within specific sites. But you'll notice that there's 2 different intercepts and slopes. So these 2 different tributaries have different distributions of our large river specialist fishes, despite broad overlap in the discharge within each system. We also see a lot of scatter at the smaller sites. And so this is telling us we're violating the assumptions of normality. We're probably missing a covariate here that is explaining all of the scatter at smaller sites. And sure enough, if we try to fit a separate model to just the residual variation that exists with that model, the best predictor of that scatter is the distance a fish might have to swim from the main stem source to a site within tributaries. The farther up you go, the more this species discharge relationship tends to fall apart, which is telling us that dispersal is an underlying mechanism behind these observed species discharge relationships. Or at least it's one of the mechanisms. So you can see this on those branches. River have far more large river species in them than we would expect to catch based on discharge alone. Those sites are accessible to those dispersing fishes. Our small isolated sites are the complete opposite. Particularly in the upper Merrimack, you will be hard pressed to find any of these large river dihadromous and petadromous fishes. They just aren't making that journey all the way up. And it makes sense. Why would they go that far up if they have found the habitats they need lower in the systems? So just some conclusion of this case study. We do support a positive species discharge relationship observed with Precho et al. We think it's a useful conservation tool. However, some caveats recognize that tributaries with vastly different availabilities of habitats may have different species discharge relationships within sites. Particularly in this case, we chose two similar sized tributaries, but with very different habitats. One has those rocky upland shoals are probably pretty useful for spawning. The other effectively is just sort of an extension of the Missouri River. It really doesn't have any whole lot of complementary habitat within it. And also recognize there's a dispersal cost. These fish are not sort of passively just moving into. It's, based on the distribution of these residuals would tell us that fish are accessing are using smaller sites with lower discharge that happen to be accessible to those dispersing fish. And this has some really very applied implications. And so when I started this, so people don't realize this, but Missouri actually has some diadromous fish. Alabama shad is a species that used to be distributed throughout the Mobile and the Mississippi River drainages. It's pretty much been, I don't want to say decimated, but the data would suggest there's been a really strong decline. In Missouri, they weren't really sure if the species even existed anymore. And we, in the Merrimack system alone, ended up catching about 80 juvenile Alabama shad through our sampling, with about 20 of those coming from the Big River, which is, ironically, one of those small branch sites that just happens to be accessible to dispersing fish. This is, I'm still involved with this. This Alabama shad was petitioned for listing under the ESA last year. The NOAA and the U.S. Fish and Wildlife Service are undertaking that species status assessment right now. And it's looking like that the last major stronghold of recruitment actually are these tributaries, are these Ozark tributaries. And so I stumbled into one of the sort of last remaining kind of spawning hotspots for this species. This is one of nature's great migrations that people don't know about. This is equivalent to like an American shad from the Albemarle Sound migrating all the way to Topeka, Kansas to find specific rocky shoals to spawn on. This Big River site is about 1,200 miles away from the Gulf of Mexico. It's a major dispersal event to get up to these sites. So that wraps up the first case study. I'm going to pivot to the complete opposite end of the streamside spectrum and talk about some of my group's work with a different type of network. These are our headwater networks. And I'm going to talk about burrowing crayfishes. So this is my group without doing a survey, very different survey of a roadside ditch in Northeast Mississippi. And shout out to the master's student who's leading this work. This is Devin Rayburn. A lot of folks have met her through NCSU's chapter of the American Fisheries Society, where she's the co-president. And she's really, I love that she studies crayfish, but she's really happy to see this spotted gar, which makes me happy. All right. So the other sort of management agency within the co-op unit is the U.S. Fish and Wildlife Service. They're our sister agency within the Department of the Interior. They've been really working through that mega petition for the last 15 or so years. One of the most difficult groups of species they're having to evaluate are 4 petition species called the rivulet crayfishes. These were in that 2010 mega petition. The species status assessment is due in 2025. And like a lot of burrowing crayfishes, we know almost nothing about their life history or patterns and population trends. In lots of risk assessment, they look for, usually there's 4 main rarity axes that they try to evaluate species, in conservation assessments. The first is range size. In this case, this is a microendemic. It's only known from 2 Huc 12 watersheds. So we sort of struck out there. The second is its distribution. So within its range, how ubiquitous is it? This species is only known from 12 sites. The third is its trends. It hasn't been caught since 2007. There's a lot of, at least some of the folks have tried to look for this crayfish, suspected that it may actually be extinct. And then the fourth rarity axis is abundance. And if you look to the description of this species, it was regarded as never abundant. And so things were looking pretty bleak for, in this case, this is the Oktibbeha rivulet crayfish. But that's okay. This is why we need good monitoring data. We need to look into it. So this species has also been noted to inhabit non-perennial streams. And so this is exclusively in the coastal plain. We have a lot of small streams that are seasonally wetted in winter and spring. And if you come back in summertime, they're completely dry. This crayfish is a secondary burrower, which means it has the behavior ability to burrow down probably about 1 meter or so deep to access the groundwater during dry periods of summer and fall. So that gave us some hope that maybe we're just looking in the wrong spot or looking at the wrong time, or those previous investigators. The problem, though, is that these non-perennial streams do not exist on a map. Like you can't open up your atlas and find the little blue line. They're not there. They haven't been georeferenced. If you go to the National Hydrography data set, they don't exist either. And if you exclusively constrain where you're looking for this crayfish, you only have about 363 kilometers of perennial streams that have been georeferenced. However, increasingly, we have really sophisticated ways of measuring the surface of the Earth. So we have LIDAR, which is available in Mississippi at 1 meter squared resolution. It's really, really high resolution data across its range. And we use some watershed modeling approaches to build our own stream networks and set the threshold on what is a stream versus not a stream at a really low level so that we can bring to life where these potential headwaters exist. And so if we go off of these own georeferenced headwaters that we mapped, there's over 1,400 kilometers of potential stream habitat for this crayfish. But we hadn't seen anyone use this technique before. We hadn't used this technique before, but we thought it was going to worth giving a try, especially since going into this, people thought this thing may be extinct. Crayfish biologists also have this habit of driving around roads and looking at good-looking ditches for crayfish habitat. If they see one, they'll get out, sample the ditch. And I thought this was a really clever way to sample these rare animals, but it drove me crazy because it's very opportunistic sampling. And in doing that, you're only sampling the best-looking spots, and so you completely distort your your interpretation of rarity at the landscape scale. So I wanted to try to formally build in a survey of roadside ditches as well, using a 20-meter buffer on all of the georeferenced roads across the species range. If we do that, there's about 554 kilometers of roads that exist. So we set this up. We did a removal occupancy design. We sampled I think it was over 180 sites just in spring of 2023. So we wanted to sample sites in the early spring when this crayfish was would supposedly emerge from its burrow. So it's coming to us versus us having to dig up those burrows. We had three main sites we were interested in examining occupancy. One was those perennial main stems. We had 36 sites. We chose 85 of those ephemeral headwater sites, and we had 64 roadside ditches that we surveyed. As I said, going into this, we really didn't know if this animal existed or not. This is sort of our blank slate. We weren't super optimistic that we would catch any. If we caught one, that was a big deal. And Devin and her group went out and actually detected this Oktibbeha rivulet crayfish at 65 sites. So she caught in about 10 of the 12 historic localities, which means she caught 45 new distributional sites of this animal. She caught them in headwaters. She caught them in main stems. And she also caught them at a handful of roadside ditch sites. So it's really exciting news, especially for the Fish and Wildlife Service that has to do the risk assessment for this animal. So this is a breakdown of a figure that Devin prepared. She ended up catching them at 18 of those perennial streams. She's caught them map sites here. She caught them at 37 of those unmapped streams, and she caught them at 10 of those roadside ditches. This also breaks this number of sites surveyed into whether they were present or not detected. She ended up having really high detection probability using the occupancy design as well over 95%. So these sort of non-detections are effectively absences, or at least local absences. And if you break this down, it comes out to be about 40% of our perennial streams we caught this animal in, about 40% of our headwater non-perennial streams we caught rivulet crayfishes, and we caught rivulet crayfishes. I think it's about 18% of those roadside ditches. So the ditches aren't quite the same level of habitat as those other two sites. But when we're thinking about this in terms of absolute availability of habitat, those roadside ditches are contributing habitats. So our sort of before-after rarity comparison, the range, well, we can't really do anything about that. It's a micro-endemic. It's still restricted. However, where we've made some pretty big differences is the distribution axis. So we thought this was a potentially extirpated animal. In reality, we caught this animal on average at 37% of the sites that we surveyed. Trends, we thought this may be a negative trend. We can't go back in time and resample to sort of get a positive trend from this, but we can say we don't think there's a negative trend going on here, mainly because we caught them at 10 of the 12 sites that we that were historical localities. And abundance, it was stated as always being rare. We found the complete opposite. This is probably the most abundant crayfish that exists in these, particularly the headwaters. That photo on the bottom left looks like a bunch of detritus that we sorted. That's not detritus. Those are actually juvenile Oktibbeha rivulet crayfishes. Just within a 10-minute standardized survey at one of the sites, Devin caught 913 individuals. You can just see like a total ball of rivulet crayfishes there in her hand there on the photo on the right. So a theme of this was developing innovative monitoring protocols, allowing those to ask us better research questions that help us manage our resources. So one of the questions that Devin is looking into is, what distinguishes a roadside ditch with suitable habitat from a roadside ditch without suitable habitat? We're using a network of 50 shallow water wells randomly selected at sites across our study to see if the underlying hydrology is actually what's driving these suitable roadside ditch habitats. We actually suspect the really suitable roadside ditches are actually former headwaters that have been ditched. So the hydrology is still there. They're still sort of functioning like a stream. They just happen to also be a roadside ditch. But we'll see once we analyze the data. And we're also interested in how much habitat has been lost through water management. So oftentimes, particularly in urbanized and landscape, there's this decision just to go ahead and completely concrete over the roadside ditch, which definitely eliminates, for the most part, any crayfish habitat that exists. And so now that we have the ability to map the background availability of these habitats, predict the suitability of those habitats, we can try to come up with some estimate of how much habitat has been lost. All right. Here's the final case study. This is taking all of this. It's a slightly different type of network. These are Bayesian networks. This is an analytical tool that's very useful for working with data poor animals. This is some work that I've been working on with the Fish and Wildlife Service on for a few years now. So the Fish and Wildlife Service, there's a species that's been petitioned. It's found to have some type of credible evidence. It'll undergo a formal risk assessment called a species status assessment. They use the 3 R's framework, which is resiliency, the ability of populations to withstand stochastic disturbances. This is inherently a population phenomenon. Redundancy is the ability of remaining populations to survive catastrophic disturbances. So this is more of a metapopulation phenomenon. And representation is the environmental and genetic diversity of a species across its range. And so this is sort of using the historical baseline, how much of the evolutionary potential has been lost since that historical baseline. So there's latter two a little bit beyond the scope of this. I'm just going to focus on that first R, which is resiliency, which is we can think about this in terms of sort of population viability. There's lots of tools to undertake the modeling of species status assessments. Most of those aren't even available in these situations where we're working with data poor animals. You can't do like population viability analyses if you don't have standardized monitoring data. It's really difficult to build species distribution models if you don't have species distributions. So instead, the Fish and Wildlife Service often likes to use a couple different tools. The first is they use flow diagramming to map the logic of what could be driving the demographics of a focal species. And so I pulled this right out of the Carolina Maritime SSA. And they often pair these flow diagrams with qualitative point scoring indices. And so what they'll do is they'll say, okay, we think that occupancy is predictive of imperilment risk. And therefore, on a watershed by watershed basis, if we think that occupancy is higher than some level, so let's say there's a certain number of occurrences, we'll sort of score that out as high. If we haven't observed this animal in this watershed, we'll score it down as low. We'll give it a value. And at the end of the day, we'll average it all to get to some type of composite index of imperilment. So I always like when we can pair sound logic with data. I think that makes for a really, really strong analysis. Some of the potential issues, though, with this approach is that the indices are inconsistent. There's no set index from one species to another. There's no set index from one biologist to another. So if you're in a situation where your predecessor developed this imperilment index, the species got listed, that person left, you're the new recovery biologist, you inherit that person's index. And so you have to use their same tool and agree with the logic they use to get to those conclusions. So there's some inconsistency across biologists and field offices in Fish and Wildlife Service. The index is not probabilistic, meaning that it doesn't really handle uncertainty. You sort of are forced to pick a value for this in situations where you may not have very strong data. And it's difficult to pair with external analyses that are probabilistic. The fourth issue is it's just difficult to communicate to decision makers. We are trained and ingrained to think in terms of chance and probability, and it's really difficult to sort of translate like an index value of a 3.5 in terms of probability of viability to those decision makers. Luckily, there's this great tool that pairs flow diagramming that's still able to follow a lot of the logic that goes in these condition indices. They're called a Bayesian belief network, and so you oftentimes see these models represented in terms of these almost looks just like a flow diagram with numbers. So for the last case study, the goal here was to develop a standardized, rapid, and defensible approach for conducting species status assessments for data-deficient fishes. We have two objectives for this last case study, and that's just to overview our approach for building a Bayesian belief network for southeastern fishes. And the second was to validate our initial model to make sure it's working the way that we think it should be working. So I'm not going to go too deep into this, but I have to kind of overview this. So what's a Bayesian belief network? You can think of it as like a model. there's a predictor variable, there is a relationship with a response variable, and there's a link that connects those two, which characterizes the relationship between those two predictors and response variables. In this toy example, I just use states A and B. This predictor variable could be the number of occurrences. And we could have some type of threshold for where we think there's a lot of occurrences, another threshold for where we think there are few occurrences. And we can put a probability based on our data that we think, let's say A represents high occurrences and B represents a few occurrences. The important key here is that we don't have to be 100% certain whether there's many or few occurrences. We can say, well, we have some reasonable data based on our sort of just collecting over the last 10 years. We think that there probably are a lot of occurrences, but we aren't quite sure. You can just build that into the predictor variable. You can incorporate that uncertainty. And you can also translate the relationships between our predictor variables and our response variables. So we can say, well, if our predictor variable is number of occurrences, and if there are a high number of occurrences, then therefore we'd expect 90% of the time resiliency would be high and 10% of the time resiliency would be low. And so you can sort of build this out, build the conditional probability to this. The predictions that come out of this model is really is the matrix multiplication of our predictor variables with our child variables. And that's the last I'm going to talk about the underlying mechanics of how this works. The important thing is you can build this piece by piece. And so you can sort of focus on one relation at a time. And then once you sort of get that one relationship set, you can build it out until you got entire conceptual and statistical model that represents our perception of imperilment. And so here, just an example, we do it on an analytical unit or a watershed by watershed basis. You can inform the top part of this model, which is based on effectively population demographics from those existing population data we may obtain from state databases. If we don't have any data, that's okay. We can just say that in the predictor variable. We can just say we have complete uncertainty, and you can still run the model anyways. And oftentimes we have better habitat data than we have population data. So if you have information like the watershed land use or water quality or anything else, you can also build that into the habitat component of this model. And the final output of resiliency incorporates both our population demographic data and our habitat data to get to a predicted resiliency wrapped with uncertainty. So the second objective was really the ground truth of the model with existing species status assessments. And so as the dude would say in The Big Lebowski, that's just your opinion, man. Like, how do we know this actually works? Which is a great point. And so because both the existing species status assessments use the 3Rs framework, and because this model is built on the 3Rs framework, we should have some pretty good congruence between our predictions using the model and those reported in the species status assessment. We statistically evaluated this with a simple classification statistic called ordinal version of Cohen's kappa statistics, with values of 0 being no or slight predictive performance. So on a scale of you're full of it, Corey, we don't believe you, to all the way down to almost perfect classification, our values between 0.8 and 1 with gradients in between. So we wanted to use existing species status assessments to validate this. All of the 3 species here on your right underwent a species status assessments. They all used point scoring indices. They all had available data that we could potentially use to provide a little bit of information into this validation. They all were pretty well documented, which is really important when we're trying to recreate the assumptions of the SSA. The first one is Ozark chub, which is a species I worked with out in the Ozarks during my PhD. It was reviewed in 2019, found to have moderately high resiliency. Ended up not being listed under the ESA. The second is a fish that was a focus of my master's thesis, the candy darter in the Appalachian Mountains, the New River drainage in Virginia and West Virginia. It was reviewed in 2019, found to have moderate resiliency, but it ended up being listed under the ESA. And the third species is North Carolina's own Carolina mad tom. It was reviewed in 2018. found to have moderate to extirpated resiliency across its historical range, and went on to be listed as endangered under the ESA. So this is the figure there in the upper right is the actual reported resiliency by the species status assessment of Ozark chub. We categorized this into high all the way down to possibly extirpated, not applicable, or places that they didn't evaluate, or watersheds they didn't evaluate. And this is what the model predicted. I find the figures are a little bit easier to interpret than just looking at a table, but you can see it's pretty good congruence. Overall, it was predicted to have moderate resiliency. Both the model and the SSA predicted the lowest resiliency to occur in the upper White River system, where there's a series of reservoirs that have fragmented the species range. You can look at the case-by-case comparison there at the table. Overall, this model had a moderate classification success, but that was highly significant. For candy darter, this is what was reported in the SSA. This is what the model predicted. So again, pretty good congruence between the figures. The model and the SSA both predicted to have highest resiliency in those high elevation northern portions of the Gauley and Greenbrier drainages, the lowest resiliency in the southern portions of its range in the New River drainage. There was overall a substantial predictive accuracy, highly significant, but there was some misclassifications going on those lower resiliency tiers, and I can provide some explanation of that a little bit at the end here. Finally is Carolina mad tom. This is what was reported in the species status assessment. This is what the model predicted. Again, you can sort of visually see there is some congruency. Both the model and the SSA reported the highest resiliency occurring in the upper Tar Basin. There are a couple stretches in the Neuse that were predicted to have kind of low to moderate resiliency. Both the model and the SSA picked up on that, but we see a lot less congruence here than we have, at least visually, with some of the other two species. And again, those misclassifications are happening on those lower tiers of resiliency. So some conclusions from this case study. We felt pretty good with this model, and that the fact that it was statistically predicting the same results of those SSAs. Each of those SSAs takes the fish and wildlife months and months and months to do. If given the data, we can run this model for each of these species within a matter of seconds. So it's far faster, it's standardized, it seems to be following the same exact logic that went into those SSAs. So we feel like this was a pretty good proof of concept. We validated it. We had anywhere between moderate and substantial validation success. We did see some misclassification for Carolina mad tom and candy darter. And we looked into this, what was driving that. What it ended up being is we were missing some structure to our models. Oftentimes with SSAs, there's this group of technical experts of the species. They weigh into, they review the SSA. They can kind of overrule the Fish and Wildlife Service's existing index. For both of these species, we had some more recent concerns about invasive species. And so oftentimes with these SSAs, they would kind of have this caveat built in where if we did some recent sampling, we didn't catch the species, we know that there are some invasive species there, we're going to go ahead and categorize that as low or potentially extirpated. So it ended up being some kind of an overruling effect that went into those SSAs. We can also build that capability into our model if need be. So overall, this also was really instructive for us to see where we're just kind of missing the ball a little bit on this. Future directions, we actually used this for the SSA of piebald mad tom. This approach is rapid enough that we actually were able to give the Fish and Wildlife Service preliminary results far ahead of the actual SSA being due. We highlighted some places within piebald mad tom's range where it actually had decent resiliency, but high uncertainty. And we did a sensitivity analysis, let them know, if y'all go in and catch piebald mad tom in those sites, it'll really influence the outcome or the predicted resiliency range wide. And so that's exactly what they did. They went in last summer, sampled these sites, ended up catching 20 juvenile piebald mad toms in a drainage that they, before that, were presumed extirpated from the entire drainage. So ended up providing some real-time feedback for them to help them guide their limited resources before the actual status assessment was released. We're developing user interface so people don't need to know the underlying mechanics of BBNs, but would allow them to just work with the Excel spreadsheet, do lots of scenario planning and sensitivity analysis to help them guide where they want to invest their resources. I think there's a lot of opportunity in recovery planning, knowing that if we can predict imperilment, we should be able to reverse engineer imperilment to help us guide what recovery actions might be the most effective to get these off the Endangered Species Act. And we've been working for the last year to build a crayfish version of this model with crayfish experts across the Southeast. Just to recap my talk, again, a couple high-level points I wanted to hit. Just demonstrate how innovative monitoring techniques can reveal hidden biodiversity patterns in riverine networks. And we wanted to highlight how information can inform conservation risk assessments of data poor species. So thinking about our role within the co-op program as helping support management through applied research and monitoring. I want to thank all the colleagues that were helping me out with these 3 case studies I overviewed, thank members of my lab. Also want to thank the fabulous photographers for their great photos that I borrowed for that last case study. The last the group that I'll thank the Wildlife Resources Commission. I'm incredibly fortunate to have an opportunity to come home after working across the Southeast, have an opportunity to take over what historically has been the program's most productive co-op units here at the North Carolina co-op units, and take over the position that Tom Kwok held for 20-some years, who I know was a mentor and a colleague to a lot of people that are on this call. So with that, if there's any time, I'm happy to take any questions.
Thanks so much, Corey. That was great. We do have one question in the chat. If anybody else has a question they want to ask, you can put that in there as well. The question is, what role does water quality play in the presence and population viability of rivulet crayfish in roadside ditches?
Yeah, that's a great question. This is sort of going to that ability for now that we're using that LIDAR and alternative monitoring approach to actually study the role of roadside ditches for supporting crayfishes. We're able to start to ask that question. We did take a lot of habitat data, water quality data, and we're going to, some of the predictors that we're interested in are dissolved oxygen, knowing that these oftentimes aren't really flowing, but they are shallow, so they should get a lot of DO exchange. Certainly looking at connectivity, knowing we don't obviously have road salts in Mississippi, but there still is a lot of higher connectivity associated with those roadside ditches. And we've looked at, we're going to test, use these data to try to test some of the potential influences of water quality. We weren't quite there yet. That'll be in Devin's master's thesis, but we can certainly formulate some hypotheses that may potentially influence ditch habitat. There's some other things that we didn't do that I'm really curious about. Some crayfish are really sensitive to certain types of metals. So looking at the type of metal composition of some of our culverts and whether that's leaching in some of these toxic metals to crayfish. Really curious about different types of macrophytes and whether they're indicators of good water quality that may occur in some of these roadside ditches. So yeah, there's lots of questions. I don't have very many answers at this point. I just kind of have some hypotheses and some predictions.
Okay, thanks, Corey.
Yeah.
And one more question. Says you mentioned that distance has had the strongest effect as a covariate in your discharge study. What other variables did you measure?
Yeah, so discharge was one of them. We also looked at the dissimilarity of habitat from at a site to a reference site out on the main stem Missouri and Mississippi River. So we were looking at discharge and we were looking at the availability of habitat. As it turns out, habitat is pretty predictive of the number of large river species or the differences in habitat of the main stem and what you find in a tributary. But that variation is already explained by discharge. This is what discharge is one of the mechanisms of discharge is creating the habitats those fish are queuing on. Because what we did here is we did a residual analysis. So we looked at the things that discharge was not explaining. And so that's where distance really came into play. And you can see the effect of dispersal distance in those really small sites that happen to be located lower in the watershed, because they are branches to the Merrimack and the Grand River. Those are just a few situations where discharge is deconfounded from dispersal distance, and that's how we were able to pick up on that signal of discharge in the residual analysis.
Okay. Well, thanks. Thanks, Corey, so much for talking today, and thanks everybody for joining. A recording will be made available. We'll let you know when that's available on YouTube. Next month, we'll have Doug Howell. He's going to join us and talk about the history and stats of resident Canada geese in North Carolina. Thanks again. Everybody have a good day.
Awesome. Thanks, y'all.